Hello and welcome to my channel. Today is number 11 of our Maker Advent calendar, and today we're going to open up box number 11. So today we're going to be playing with a really fun and useful component that you can use again and again in your projects, a mini I2C OLED display. This is what it looks like, very teeny tiny. These little displays are great for showing data from your project, such as a sensor reading, score, pin status, alerts, and other useful information. We're going to combine it with some components from earlier boxes to show you just how handy these are. So let's go. So inside this box, we have a pre-soldered 0.96-inch OLED I2C display and 4 male-to-male jumper wires. So today we're going to display data on our mini I2C OLED display. They're relatively easy to code, but they do require the installation of a library, which we import at the start of our program, but we'll guide you through this. The display in your box is an OLED display. OLED stands for Organic Light Emitting Diode. You may have seen this mentioned on advertisements for TVs, as many models use this technology. It's a type of digital display technology that uses LEDs and layers of thin organic film between two electrodes. When electrical current is applied, the display emits light. Our code tells the display where to show light and when. So I2C, sometimes referred to as IIC, stands for Integrated Circuit. It's another type of communication protocol which allows multiple I2C devices to communicate to a controller like our Pico. I2C requires just 2 wires to communicate and has the benefits over some other communication options, but we won't bore you with that just now, as it's not going to be relevant until you're much further along in your Maker journey. To use I2C, we need to import it in our code, which we'll show you how to do in just 2 ticks. So let's construct the circuit. Firstly, disconnect your Raspberry Pi Pico from your PC, ensuring it is powered down. So let's unplug the Pico. Today, we are finally removing the LEDs and buzzer as input components. Today, we are finally removing the LEDs and buzzer as input components are more relevant and useful with this display. If you haven't already, remove everything so that you're back to a clean breadboard with just the Pico like this. So let's just remove all the wires. Now I would suggest putting the resistors and the LEDs in the same bag so you don't get them muddled up with any other resistors that you've got. And then let's just remove the buzzer. Okay, so next, fit one of your buttons and the OLED display into the breadboard like we have below. You may also want to peel off the display's protective film at this stage. Okay, so the buttons were in box number 3. So I'm just going to grab them out. I'll put everything back in the boxes that they came in. So I just need 1. So tricky. There we go. 1 button. Okay, there is a protective film on the OLED screen, so let's take that off. And we are going to add the pins like so. Next, we'll add our 3.3 volt connections, run a jumper wire from physical pin number 36 to the upper red channel. So pin number 36 is that one to the upper red channel. Then connect the left button pin to the same red channel. And the second OLED pin labelled VCC to the same channel as well. VCC. Okay. So next is our ground pin. Connect the first OLED pin labelled ground to the nearest ground pin. So that's 18. Okay, so we've got that hooked up like that at the moment. Now for the 3 GPIO pins which will talk to our Pico. Connect the right button leg to pin number 11. So the right button leg to pin number 11. Connect the third OLED pin to physical pin number 2. Connect the fourth OLED pin to pin number 1. And we should have something like this. We'll be using the light sensor from box number 6 in our examples today, so we need to wire that up as well. We'll use our mini breadboard for this. Fit the light sensor and the resistor into the breadboard as we have below. The long leg of the light sensor needs to go on the left. So we've done that here. Now to wire up the light sensor to our Pico. Connect the left resistor leg to the ground connection on physical pin 28. Physical pin 28. Connect the left light sensor leg to pin number 31. And connect the right sensor leg to physical pin number 36. Now turn your breadboard 90 degrees so the OLED is facing you. To install the code libraries, plug your Pico back into your computer's USB port and make sure it's recognized. Then let's install what we need to make this display work. Okay, so I'm going to plug that in now. Our display needs a code library package that isn't included in MicroPython by default. So we need to install that before we can start using this display. We will then import this library when we write our code. Luckily, this is very easy to do and all handled within Thonny. So let's get it installed. The following may vary slightly depending on the type of computer you're using. If the steps below don't work for you and you see certificate errors or other similar messages, you may need to install the library manually. So, first of all, in Thonny, from the top menu bar, select Tools. We need to stop, pick up the Raspberry Pi, go to Tools, Manage Packages. You should see something similar to the box below. In the search bar, enter MicroPython-SSD1306, then select the search button. You should see results like we have below, including the MicroPython SSD1306 module we need at the top of the list. Select that line to go to the information screen for that module and then select Install. Once the package has installed, it will show on your installed packages list on the left. It's now ready to use. So activity number 1, simple text display. We'll start by showing a single line of text on the display to kick things off. Of course, it will be the traditional Hello World. I2C and display setup. To use this display, we need to import I2C as well as the library we have just installed. You'll see this in the first few lines along with other imports as always. We then need to set up I2C and the display, which you'll see on line 7. This includes the GPIO pins we're using, GPIO 0 and GPIO 1, which are the SDA and SCL pins used for I2C connections. After this line, we always have to wait around 1 second, otherwise I2C can get stroppy and fall over. Next, we define the display size in pixels and the type of driver chip it uses. Our display uses an SSD 1306 driver and is 128 by 32 pixels, which is reflected on line 13. That's all set up out of the way. Displaying text. When we want to display something on the display, we always go through the same process. Clear the display, define what content we want to show on the display, push the content to the display. If we don't clear the display every time, it will write the new content on top of the old content, which makes a big mess of jumbled up characters. Our example shows us clearing the display with display.fill, then sending hello world with display.text, and finally pushing this to the display with display.show. We'll cover what the 00 arguments do in the next activity, but for now, copy this over to Thonny and see it for yourself. So let's copy the code, paste it into Thonny, and run. So as you can see, hello world. Activity 2, multiple lines of text. Let's go one step further, adding more lines and changing the position of the text, but first let's cover those arguments. You'll notice there are some arguments, 00, after the text we push to the display. Display.text, hello world, 00. The first argument determines how many pixels across the display the content should start. And the second argument determines how many pixels from the top the content should start. Our display is 128 by 32 pixels, so we have 128 pixels running across on the x-axis and 32 pixels top to bottom on the y-axis. In our example below, we've managed to squeeze 3 lines of text on our setting, each one at a different height, which just takes a bit of trial and error. The first line is 0, the next line is 12, and then the final line starts at 24. If we add more lines, they won't be fully visible. We've also moved line 2 over to the right by entering 50 for the first argument again, just with trial and error. Give the example below a try, and then have a play with the argument values to see the changes for yourself. So let's copy, paste, stop, start. So in the code, it's going to display line 1, line 2, and line 3. Can we see that? And you can see how line 2 is indentated all the way over to one side. So activity 3, the endless counter. Small OLED displays are great for displaying data, and they can refresh quickly enough to show data changes at a very fast rate. Let's create an endless counter to show another way of using these displays. When you come to make your own projects, things like this will be very useful. We don't use any physical inputs here, just a counter in our code that increases by 1 every loop. A new problem, our counter is a number, an integer, but our fussy little display will only show text, a string. So we need to convert our counter to a string every time we run the loop. Converting integers to strings. We convert the counter integer to a text string using the following line: display.text str counter 024. So instead of entering text in brackets like we did in the previous activity, we used a string counter to turn our counter variable into a string for our display. It's otherwise quite straightforward, adding +1 to our counter at the end of every loop to continually increase it. You can play with the time delay within the while loop to just see how that runs. Let's copy the code, paste it into Thonny, stop and start. The endless counter, it's called. Can we see that counting? Activity 4, the naughty or nice game. We're now going to create a game that decides your festive fate. Let's make a naughty or nice game, which will tell you if you're on the good list this year or not. This project shows naughty and nice with a marker that very quickly switches between the two. When you click the button, it stops on whatever option the marker is on at that moment. Your aim is to land on nice. Our example below uses all of the usual ingredients and creates a state variable, which we've used before. We use this variable to switch between the two if statements within our while loop. But why do we want to do that? We want our display to constantly move the marker between naughty and nice. To do that, we have two if statements which are triggered by a state variable being either 0 or 1. Each if statement starts by showing the text with the marker at a different position. If the state is 0, the text pushed to the display shows the marker on naughty. If the state is 1, the marker is on nice. Each if statement also changes the state so that the next loop, the other if statement will trigger, which makes the marker jump between the two. Each of the if statements then has a nested if statement inside it which checks if the button is pressed at that very moment. If it is, the code inside it updates the display to confirm which option was selected, followed by a second pause. So let's copy over the code, paste, stop, and start the command. So it's flashing naughty or nice. So if I click the button, oh, I've been naughty. Let's click again, and now I'm nice. Naughty. Yay, I've been nice. Activity 5. Show me the light. Showing sensor readings on your OLED is quite possibly one of the most useful and fun ways to put the display to good use. We're going to run an example where we continually check the light sensor reading and push this to the display. It can even show the percentage symbol. The example below includes similar code from the light sensor box in day 6 and some OLED display code, an approach we've taken above. So most of this should make sense if you've been following along. The same initial OLED imports and setup code is present, and we've added the light sensor pin setup back in, linking it to GPIO 26, along with the required ADC import. We then start a while loop, which takes a reading from the sensor on line 25. Now, this line does a lot of things at once, so let's break it down. It creates a variable called light, it takes a sensor reading, it turns the reading into a percentage, and it rounds the reading percentage to 1 decimal place. We did something similar on day 6, but this time we're doing everything in a single line of code. We've avoided this so far, as it can be a little overwhelming, but we're on day 11, so we think you'll be okay. We then push this data to our display. We use the first line of the display to show some simple text, and the second line to show the reading. Just like the previous examples, we have to convert our light variable to a string to allow the display to use it. We also add the percentage symbol to the end. So let's copy the code again. Let's paste it into Thonny, stop, and then start. So the light level on the display is shown at 23%, 50%, because I've tilted it towards the window, I guess. Aren't OLED displays just bags of fun? We've only just scratched the surface as well. There are lots of clever ways you can use these kinds of displays with graphics, fonts, and other tricks, but we wanted to keep our activities relatively simple for beginners. You'll find a ton of resource and other examples on the internet that you can use. We even have our own graphics tutorial which can apply to these displays too. So let's recap, what did we learn on day 11? Today we learned how to wire an OLED to our Raspberry Pi Pico, introduced the I2C communication protocol, learned how to install packages to Thonny, learned how to code I2C OLED displays, including how to write text to the display, how to write multiple lines of text, how to alter the position of text, how to display sensor data on the OLED displays, reused knowledge and components from previous boxes such as state variables, converting integers to strings, nested if statements, and light sensors. So we're one day away from our final box, and I'm getting really excited. So I really look forward to seeing you guys tomorrow, see what's in store for us.